A warm welcome to everyone. I'm standing before you today as the head of Department of Mathematics at King's College. And the reason that I'm standing here is that on the 17th of September, which is just under 4 weeks ago, I received an email from the strategic consultancy lead at Wolfram Europe, telling me that Stephen Wolfram was going to visit the UK imminently, and asking if we were interested in organizing an event at King's. So this, of course, was a rare opportunity for us, and the exciting ideas of actually organizing this live event, where Stephen could just share with us his insights in mathematics, physics, and computation, started to take shape. From that moment, we joined forces, the math department and some key people in the department, we joined forces with the Institute for Artificial Intelligence at King's as well. And we tackled what initially seemed unsurmountable in terms of logistics. All the big auditoriums in the university were occupied at all the times that our guest was available, and therefore it required a little bit of creativity, and that obviously worked since we are here in the room today. By the way, I want to thank all the people who contributed to, let's say, the preparation of this event. It's a textbook example of constructive collaboration between academics, professional services, and technical staff in King's. And it's a wonderful demonstration of, yes, we can. Yes. I will shortly hand over to Professor Rachel Barron, who is the Executive Dean of the faculty NMES. She is Professor of Mathematics, and she will introduce briefly Stephen in a minute. But before that, I will take another minute to share with you and with Stephen a small, tiny connection I have with you. Many, many moons ago, in 1980, I believe, we were at the same conference in theoretical physics, and you came to give a talk, and I was in my first year of PhD. And already then, when you arrived in the auditorium to give your talk, you were quite young at the time. And there was this buzz going on, a wave like this in the audience, because we already knew that something was being cooked up in terms of what became Mathematica, of course. So I met you there, and of course, you didn't probably meet me because I was in the audience and you were talking. But that's my connection. All right.
Thank you.
Rachel.
Thank you, Anne. And again, warm welcome to all of you today. I won't talk very long because I know we're all keen for the main event. But I did just want to highlight what an honor it is. We have some fantastic visitors who come through King's. And today we really are very honored to have Stephen join us. I think the wealth of experience that he brings really chimes with many of the things that we care deeply about at King's and in our faculty. In knowledge creation, how we are curious and discover things. In innovation, how we translate that into things that have real impact and have impact both in terms of society but also economic impact. And also communication. We're all passionate about sharing our knowledge, about our education, and about communicating to the wider world. So Stephen, I think, has a wealth of experience and evidence of how to do this well. As a child prodigy, he was publishing in theoretical physics in his teens, that knowledge creation. As an inventor, he created Mathematica, Wolfram Alpha, and Wolfram language, and translated that as a business leader to being the CEO and founder of Wolfram Research. He's also communicated this work. He's an author of several popular science books and a TED speaker. And I'm really excited today about what we're going to learn from your talk. So thank you so much for coming to King's and joining us.
Thank you. All right. Well, I wanted to tell you about a number of things in physics, mathematics, AI, and actually also biology, because there's a kind of a grand unification that seems to have been happening in the last 5 or 6 years, was kind of sparked by a project that I had been sort of planning to do for several decades, and finally actually got initiated as a result of 2 young physicists pushing me to finally do this project. One of them, a chap called Jonathan Gorard, was actually a student at King's. He'd just finished at the time when he was really pushing me to do this. So that's a small connection here. Okay, well, the thing that I've spent my life kind of alternating between doing basic science and doing technology development. It's been a very fertile thing because I've spent years building technology and building tools which allow me to do more basic science. Then that basic science has ended up developing ideas that let me figure out how to make more technological tools and so on. So I want to tell you about some things that I discovered in the last few years using Wolfram language, using this whole technology stack that we've built and interacting with it. So, okay, where did this start? Well, back when I was a kid, I used to do particle physics and cosmology and things like that. And at some point, I got curious about what seemed like a very obvious, simple question, which is, how does there come to be complicated stuff in nature, in the world, and so on? And I thought that's a very straightforward question. One should be able to use methods from mathematical physics, all these fancy things, to figure that out. Tried to do that. Tried to figure out things about, why snowflakes grow in the kind of patterns they do, or why turbulent fluids work the way they do, and was very unsuccessful. So this is beginning of the 1980s. I kind of started thinking about, well, what's an alternative way to make theories of things in science? And started realizing that, well, we have kind of a very sort of specific set of approaches to doing that using mathematics and mathematical equations and so on. What's the most general kind of a way that we could make a theory of things? And so I realized that, well, programs are a much more general way to make theories of things. Programs sort of define rules. You specify the rules by which something operates, then you let those rules run, and you see what consequences they have. So the question then came up, well, okay, if you're looking at simple programs, there's sort of a very basic science question, which is, what do simple programs typically do? It's a field that I now call ruliology, the study of simple rules and what they do. And so there's sort of a question. When we think about programs, typically we think of programs that we write for some specific purpose, but imagine the sort of basic science question of what do simple programs typically do? So, okay, here's an example of a typical, very simple program. This is a cellular automaton. I've studied these a lot. They're particularly convenient to visualize. The idea is you have a grid of cells. Each one is either black or white. You have this rule at the bottom that says at every cell, what color should it be based on the cells above it and to its left and right. So, very simple rule. In this case, very simple behavior. Start off with one black cell, you just get this uniform area of black. Well, okay, try a different rule. This one, you make one change to the rule, you get a slightly more elaborate pattern, a checkerboard. At this point, you might say there's going to be a theorem that says if the rule is simple enough, the behavior of the system will be correspondingly simple. That might be a theory. Okay, then you actually do the experiment. We could do it in real time here, but let me just show you the result. This is just enumerating all possible programs of a very simple kind. Each picture corresponds to a different program, a different one of those arrangements of what the outcome bits are for the rule. And most of the time, you get rather simple behavior. But then there's my kind of all-time favorite science discovery, which is rule number 30 here. So this is what it does. There's the rule for it at the bottom. You started off from just one black cell at the top, makes this pattern. You might say, as I did, well, the rule is simple enough. It must be the case that somehow it will eventually resolve, the pattern will eventually resolve to be something simple that we can understand. Well, so you keep running it a bit longer, and that's the result that you get. So this, it's something where you can see a certain amount of regularity over on the left, But if you look, for example, at the center column of cells here, it looks, for all practical purposes, completely random. In fact, it's the pseudo-random generator that we used in Wolfram language for many years. So it's a very surprising and, to me, intuition-breaking kind of thing that a rule that simple can produce behavior this complicated. And I think the big exciting thing here is this gives one an idea of sort of a secret that nature can be using to make complicated things. Just in this computational universe of possible programs out there, it's very common to actually find programs that produce very complicated behavior like this. So you can go and explore that. You can sort of go out into the computational universe. We could do that maybe we'll a bit later, and just go find programs that have never been looked at before. This is kind of ruliology is a very wide open field that you can easily discover things that have never been discovered before, and you often find very complicated behavior. What can we say about this complicated behavior? So one thing you can ask is, can we predict what's going to happen in the end here? You know, one of the things that has been sort of a big point in sort of mathematical approaches to science is, well, we have some equation for how something works. We can solve the equation. We can figure out what is the formula that works out the solution to that equation. If I've got, let's say, a two-body problem of an idealized planet going around an idealized star, we can just say, we can solve that equation. We don't have to follow a million orbits of the planet. We can just say, fill in a number in this formula and say, after a million orbits, this is where the planet will be. So we're kind of used to this idea that once we have the rules for the system, once we have the equation for what's going to happen, we can somehow solve it and jump ahead and say, this is the outcome that's going to occur. Well, does that work in this case? Clearly, if we wanted to know what will happen after a billion steps or something of this particular rule, we could just run it for a billion steps and see what happens. The question is, can we do any better than that? And the answer, in general, is no. In general, there's a phenomenon they call computational irreducibility that says the only way you can know the outcome is effectively to run all the steps and see what happens. So it's something which kind of violates what one hopes for in kind of predictive science. It's something where to know the answer, you basically just have to watch it happen and see what it does. I could say, by the way, that there's sort of a deeper principle that computational irreducibility comes from, which is what I call the principle of computational equivalence. If you look at all these different kinds of systems, you can think of all of them as doing some kind of computation. You start from some initial condition, you're kind of crunching through, computing what happens. And the question is, how sophisticated is that computation? You might have thought, if you have a sufficiently simple rule, like Rule 30, for example, that you would have a computation that got done that was somehow correspondingly simple. I don't think that's the case. I think instead, above some very low threshold, kind of all of these different systems do computations that are of equivalent sophistication. Well, so what? There are many implications of that, but one of them is, if you think about what does the process of prediction consist of? It's like the system is doing its thing, and you're trying to predict what it's going to do. So you are yourself sort of a computational system. You as a computational system are trying to outrun one of these simple systems and figure out what it's going to do. Well, the principle of computational equivalence says that's not going to work. It says that you as a computational system will typically be equivalent in your computational sophistication to the system itself. So you don't get to outrun it. And that's kind of the source of computational irreducibility. Well, okay, so there's a lot one can study about simple programs, what they do. You can look at all sorts of different kinds of simple programs, Turing machines, things like this. One of the sort of tests of how sophisticated a computation you can get is, can you make a universal computer out of these things? And I've sort of spent quite a bit of effort finding the simplest universal machines of various kinds I could show you. But let me go in a different direction and talk a bit about physics. So the question is, what is physics underneath? In the 20th century, we've learned a lot about physics. There are really three big theories of physics that emerged in the 20th century: general relativity, theory of space-time, quantum mechanics, and statistical mechanics, particularly the second law of thermodynamics. Those are the sort of three big pillars of 20th century physics. Well, the question is, what's sort of underneath these things? And actually, let's talk about the second law of thermodynamics first. So the second law of thermodynamics is all about if you have like molecules in a gas, you put them in a box, they'll, even if they start off in a very orderly configuration, they'll typically become more apparently disordered. They'll apparently kind of randomize in their configuration. That's kind of the idea of the law of entropy increase and so on. Well, so the question is, why does this happen? And this has been a bit mysterious. It's textbooks have a habit of sort of saying, well, one of the issues is that it seems like things are getting more random over time, but yet the microscopic dynamics of the molecules bouncing around are reversible. So in principle, at a sort of microscopic scale, you can run the movie in reverse, and that's just as valid as running the movie forwards. But in practice, we tend to see things that go from ordered states to very disordered states. Where does that irreversibility and so on come from? Well, you can kind of make a space-time picture of those molecules bouncing around. You can kind of simplify how it works a bit. Eventually, you can get down to something which is actually just one of these cellular automaton systems. It's reversible, so there it's going down successive panels here. Somewhere in the middle, it has a very simple configuration. You go forwards in time, it kind of grinds itself up to correspond to something that looks quite random. If you go backwards in time, the same kind of thing happens. What's happening is we're having this sort of irreducible computation that's generating the output. In principle, we can take the output and just go back, reverse the computation, get back to what we started from. The point is that observers like us, who are computationally quite limited, can't do that computation, can't do that irreversible, that irreducible computation. So to us, when we see kind of the output there, it looks, we just have to say, oh, it looks kind of random to us. It looks typical of the ensemble of all possibilities. It doesn't look special as something that would have come from that very simple initial condition. So computational irreducibility combined with the kind of computational weakness of us as observers is what leads to the second law of thermodynamics. So it's an interesting case where a law of physics is kind of a consequence of the way we are as observers. And that turns out to be something which we'll see that theme come up several more times, that the kind of the interaction of our nature as observers with underlying computational irreducibility leads to certain kinds of things. Now, for example, back when people were first talking about the second law of thermodynamics in the 1860s and so on, I think James Clerk Maxwell was a professor here back in those days, and he was working on the second law of thermodynamics. And actually, another chap, Kelvin, came up with this idea of the heat death of the universe, that over time, all of the kind of organized stuff that's happening now in the universe would kind of run down, and all that will be left is kind of random heat of molecules sort of bouncing around randomly. And the thing to realize is that that isn't actually the right picture, because it only looks like random heat if you're an observer like us. In the future, if you have a very different kind of observer who is more computationally capable, that configuration of molecules in the future might be easily recognizable as sort of the future of the things that we're doing now. So again, this kind of the idea that the laws of physics depend on the nature of the observer interacting with this underlying computational irreducibility. Okay, well, let's talk about fundamental physics. I think I was just starting to get into that. Question is, what's the universe made of? And we've been a little bit pessimistic, I think, in the last probably 50, 100 years, that we're not going to figure that out, that it's going to be continued. We keep on getting to greater levels of smallness, and we keep on having sort of more and more new physics shows up, and we can't ever get to the bottom of the whole thing. Well, I think we actually now have a pretty good idea of what's at the bottom of the whole thing, so to speak. But let me start with kind of a question that came up in antiquity, which was, is the universe discrete or continuous? There were sort of the atomists who said everything's made of discrete atoms. There were people like Heraclitus who said everything sort of flows like water. That question sort of flopped around for centuries until the end of the 19th century, when it was discovered that matter is discrete. Matter is made of discrete molecules, atoms, and so on. And then it became clear you could have photons of light that would be also discrete. Early part of the 20th century, most physicists thought space would turn out to be discrete, but they couldn't make it work. It didn't seem to be consistent with relativity and things like that. So it turns out that actually we did figure out how to make that work. And it's the first key thing to realize is that there's you can think of everything in the universe as being features of space, and you can think of space as being made of something. So what is space made of? We just think of there being discrete points, kind of atoms of space, and the only thing you can say about those atoms of space is how they're related to each other. So you could say, which atom of space is friends with which other atom of space. In the end, you're building up a graph. Actually, it's convenient to think of it as a hypergraph where you can have edges that don't just have two ends, but have any number of ends. But basically, the idea is you're building up something where there are relations between these atoms of space. And a little bit like in a cellular automaton, you have just a rule that says when you see a little piece of network that looks like this, transform it, let's say, into a piece of network that looks like that. You apply this rule over and over again. You build up this larger and larger network. You can use different rules. You build up different kinds of networks. Just sometimes, here's an example of a rule where you can kind of see what happens. In the end, you build up this thing which is kind of just like a two-dimensional fabric. You're kind of building up something which looks like a piece of two-dimensional space. And you can pick a different rule. You'll find different kinds of behavior. The idea is that what at a microscopic scale is just this graph being rewritten on a large scale behaves like continuum space. It's kind of like what happens in a gas where you have molecules bouncing around which are discrete at a small scale, but at a large scale you have fluid dynamics and the thing behaves like a continuous fluid. I think the same kind of thing is true about space, and what in a fluid might be a vortex or something, an eddy, is something like a particle in physical space. So there's a lot when you look at molecular dynamics, discrete molecules bouncing around, you look at what the continuum limit of that is. It's the equations of fluid mechanics. When you ask what is the continuum limit of these discrete graph rewriting kinds of processes, the answer is it's the Einstein equations which describe the structure of space-time. Well, there are many footnotes to that statement, but one of them is that in these models, there's a question of, well, okay, you've got some complicated network. You say, well, what dimensional space does this correspond to? Is it one-dimensional, two-dimensional, 2.5-dimensional? What is it? You can kind of estimate the dimension of something by saying, take this graph, start from a point, go progressively one graph distance away, two graph distances, three graph distances, and so on. Just ask, how rapidly does that ball that you're building up in the graph grow? If it grows like r to the d, then d is your estimate of the dimension, the effective dimension of the graph. So in our models, dimension is a sort of dynamical parameter, so it can vary. So for example, in our models, we expect there to be dimension fluctuations in the universe. We expect that the universe probably started infinite dimensional, gradually sort of cooled down to be three-dimensional. We can't derive the number 3 yet. But we do expect that one of the sort of predictions of these models is that you will have fluctuations, perhaps left over from the cosmic microwave in the time of the cosmic microwave background, where you have regions of the universe that are sort of 3.01 dimensional and so on. Actually, I have to say one thing about that. There are many kind of sort of connections to kind of experimental ideas about physics, but I might mention one of them, which is there are lots of mysterious things in physics, like dark matter, for example, is a mysterious thing. I have a suspicion about dark matter. I don't know if this is true yet. Hopefully we'll know in the next few years. But if you go back to the history of physics, in the 1800s, people were really wondering, what is heat? Well, they didn't know, but they knew it flowed from one thing to another. And so they thought, well, what flows from one thing to another? It must be a fluid. So they had the idea of caloric fluid. And turns out heat isn't a fluid. Heat is the microscopic motion of molecules and so on. Well, my guess is that dark matter isn't matter, and that in fact it is the pretty direct analog of heat, but in the structure of space-time. So once you have a discrete model of space-time, there is the possibility that you have all sorts of microscopic dynamics of the internal structure of space-time. And my guess, may or may not be right, is that dark matter is actually a large-scale manifestation of that, just as heat is a large-scale manifestation of the motion of molecules. Well, let me see. I might have a picture here. Does this work? Let's see if this works. Maybe it works. Okay, this is a very toy version of a very tiny universe kind of growing according to these kinds of rewrite rules. The fact that it's wobbling around and so on is just a matter of the visualization of it. The only thing that actually sort of matters to the universe is the connectivity of these different elements. Okay, well, so there's one thing. So what we're saying here is that from this sort of discrete graph rewriting, we can derive the Einstein equations, the structure of space-time. We can talk about lots of phenomena that are known in general relativity and so on, have very mechanical characteristics in our models. Like, for example, time dilation. When things move fast, time seems to run slower. That's basically happening because when you have something like a particle and it is in one place, it is sort of updating itself by following a certain set of computations. If you move it, it's going to use some of that computation to recreate itself in a different place in space. And so the fact that when there's motion, when there's recreation at different places in space, time runs slower. And that's the sort of mechanical origin of time dilation. You can sort of do that much more mathematically, but that's the sort of mechanical way of understanding it, which we really haven't had before, a mechanical way of understanding something like that. Well, let's see. So another big, here's another one of these pictures. This is a simulation in discrete space-time of two very tiny black holes kind of dancing around and eventually merging and apparently producing gravitational waves that seem to agree with what you get by doing elaborate simulations in general relativity. There's many, many footnotes to this whole story, but this is at least a good indication that we can reproduce kind of the phenomena of general relativity from these discrete models. Well, that's general relativity. The other big thing in physics is quantum mechanics. I mentioned these three big areas of 20th century physics: statistical mechanics, second law of thermodynamics, general relativity, and quantum mechanics. Well, one feature of this graph rewriting kind of idea is when you're rewriting this graph, there are actually many different places where you can apply these rules. There isn't just one thread of history. There are many threads of history. So we can draw, we call a multi-way graph that shows the different kind of threads of history, the different possible rewritings that can happen. And so, we can have, I think this is a simulation of that. So this is showing kind of how one branches into different branches of history. And we're seeing kind of these are each different branch is a different possible state of the universe. Actually, one thing to notice is at a particular time, there's kind of a slab of possible states of the universe. And those kind of pink lines show kind of the connections between related kind of histories of the universe. So there's this notion of what we call branchial space, which is a space of possible branches of history of the universe. Well, we can, if we make a simpler model of one of these multi-way graphs, just with rewriting strings, for example, we can take a slice through this and we can say, what is the relation between different strings in this kind of set of branching histories? And we can define this notion of what we call branchial space. We can take the limit of a very large number of rewrites and we can say, this is the sort of geometry of branchial space. Okay, the basic claim is that in quantum mechanics, there are these laws of quantum mechanics. But basically, this phenomenon of many threads of history is the fundamental phenomenon of quantum mechanics. The fundamental difference between classical physics and quantum physics. In classical physics, you throw something that goes in a definite trajectory. In quantum physics, there are many paths that are followed, and you only get to know probabilities of different things happening. Well, that's what's happening very directly here. There's a question of kind of how do observers of this work, and it's kind of a funky thing because the observer is part of the system. So the observer's mind is also branching and merging, just as the structure of the universe is branching and merging. And so quantum mechanics becomes kind of the story of how does a branching and merging mind perceive a branching and merging universe. But one of the things that I think is really, really cool is that in space-time, we have this result of Einstein's equations, and we have things like gravity. We have gravity has to do with the fact that that sort of shortest paths between here and there get deflected by the presence of energy and momentum, by the presence of mass. That's kind of what gravity is. It's a deflection. That's the interpretation in general relativity, that gravity is a deflection of shortest paths by the presence of mass or energy and momentum. Well, turns out that it seems that the path integral in quantum mechanics, which is sort of the core of quantum mechanics, is actually the direct analog of the Einstein equations, but played out in branchial space rather than in physical space. The presence of energy and momentum in branchial space deflects kind of paths in branchial space, and it ends up with something that seems to correspond to the path integral. So this is kind of in these models, kind of quantum mechanics is inevitable, and it seems that the core laws of quantum mechanics sort of again inevitably emerge, just like just like statistical mechanics, just like general relativity. Okay, okay, so one question you might ask is, okay, let's say this all works out, and we've got this rule that we say you run this rule long enough, and it'll make our universe. Then the next question will be, well, why is it that rule and not another rule? So it had me very confused for quite a while, until I realized that just as I mentioned, you have a particular rule, and there are different places that it can be applied in this structure that represents the universe, we can also say, well, what about just applying different rules all the time? So then you can imagine sort of the limit of that. We call it the ruliad. It is the entangled limit of all possible computational processes. So you imagine applying all possible rules in all possible ways. You might say, how could anything interesting come out of that? It's such a big, complicated thing. But what you realize is when you're applying these different rules, you can have two different rules you apply. That leads to a branch. But then sometimes the states that they produce will actually be the same. So you'll merge again. So actually, let's take a very simple case. Let's look at a Turing machine. There's a Turing machine. It has little rules. So the Turing machine, unlike a cellular automaton where every cell gets updated every step, in a Turing machine, there's just this head that moves around in the Turing machine, and only that cell gets updated. So it has rules like this, for example. That's what it does. You can make a multi-way Turing machine where instead of there being a definite rewrite, there are several possibilities, and then you have these different paths of history in the Turing machine. Now you can say, well, what happens if we look at all possible Turing machines? What happens if we look at sort of the graph that we get from all possible histories of all possible Turing machines, and we end up getting some complicated thing that is one representation of this object we call the ruliad? And actually, there's well, let me not get into a sidetrack about P versus NP, but the red part and the blue part correspond to deterministic computations, P-like computations versus NP-like computations. And there's a rather interesting direction for geometrization of questions like that. But in any case, the main point is that you get this thing we call the ruliad, which is this entangled limit of all possible computations. It's a unique object. There's just one of it. Once you have the idea of computation, you necessarily can kind of take this limit and get the ruliad. So then the question is, well, what do we, if the ruliad is sort of everything, and we are part of the ruliad, what will we perceive in the ruliad? And what we realize is it depends on what we are like. If we have certain characteristics, then we will perceive certain things in the ruliad. So in particular, if we are computationally bounded observers, and we are also observers who believe we are persistent in time. So we believe we have this thread of experience that continues through time, which is kind of a crazy belief because we're made of different atoms of space at every moment. Yet we have the inner feeling that we have this sort of consistent sort of thread of experience. With those two conditions on us as observers, it seems to be inevitable that our perception of the ruliad will correspond to the laws of physics that I was just describing. All three of the main laws of 20th century physics seem to emerge from the fact that we are observers of the kind we are, sort of operating within this ruliad object. This, to me, is very sort of intellectually and philosophically interesting because I'd never thought that the laws of physics would be derivable. I thought maybe the second law would be derivable from underlying mechanics, but general relativity and quantum mechanics always seemed like things that were just, it happens to be that way. There's no derivation. It now seems that because we are observers of the kind we are, it is inevitable that we get laws of physics like this. Well, you can kind of go and try and ask, sort of in the ruliad, what else is there? Here's a fun example. This is sort of parameterizing the ruliad by using a generative AI to make make images, and we say, here's a, first of all, it's like make an image of a cat in a party hat. Okay, that's the center of this picture. But then you say, well, look at what happens in the space of possible images away from the point that corresponds to that specific thing you asked about. And what you get is sort of a cat island of places where the cat concept is easy to recognize for us humans. And then you have this vast kind of interconcept space between the things that we have given names to, the kinds of things that we have words for. There is sort of all the things that the AI can imagine. And that's sort of a little bit of a sense of what's out there in the ruliad. And it's a bit humbling for us because the concepts, the things for which we have names, represent some tiny 10 to the minus 1,000 fraction of what's out there in the space of possibilities. Well, let me mention, I said I would talk a bit about mathematics. I'm going to try and speed talk about mathematics and then about biology, and then hopefully we'll have some time for discussion and questions and so on. Let me talk a little bit about mathematics and about the foundations of mathematics. And it turns out that there's a great commonality between the foundations of mathematics and the foundations of physics, another thing that I've been rather excited about. So how do we make sort of a minimal model for what's happening in mathematics? Obviously, in building Wolfram language and Mathematica and so on, I've had the chance to think a lot about what are the primitives that underlie mathematics and other kinds of things that we can think about computation. I mean, just to say, it's just to sort of a comment. I mean, what we've tried to build in Wolfram language over the last 40 years is basically a way to think computationally about everything in the world, whether a way to kind of have a kind of a representation, just as people invented, mathematical notation to have a sort of streamlined way to talk about mathematics. Wolfram language intends to be a streamlined way to talk about computational kinds of things. And I think the big story of this century, I think, in science and lots of other places, is the emergence of kind of computational X for all fields X. And our kind of goal is to be the language that makes that possible. And there's lots to say about that, but that's not what I was going to talk about here. So let me go on and talk about foundations of mathematics. So let's say we have an axiom system that we try and make. This is some potential axiom system for mathematics. We might have, it might be, this isn't commutativity, it's something more general than commutativity, but it's something like that. So given that axiom system, it defines various equivalences between expressions. So every line here represents an application of that axiom to make an equivalence between two expressions. Well, then these are all equivalence expressions, and that path that I'm showing there corresponds to a proof that one expression at the top is equal to the expression at the bottom. So you follow that path, and you can show that's the proof that one of these expressions is equivalent to another one. Okay, well, you can then ask the question, if you just look at the axioms of mathematics and you start making sort of this object that is all possible theorems of mathematics, what does that look like? We can do that, for example, for Boolean algebra. Here's starting in green are some axioms of Boolean algebra, then we're building up possible true theorems of Boolean algebra. Okay, we keep doing that. We build up a huge number of true theorems of Boolean algebra. Most of them we don't care about. Most of them are theorems which are kind of trivial lemmas, corollaries of other things. In the space of all possible theorems, I just made dots for two theorems that are named in textbooks of logic. So in this meta-mathematical space of all possible theorems, a small number are ones that we pick out as interesting for human mathematics. And you can kind of map this out a bit. There's some famous theorems of mathematics kind of mapped out in meta-mathematical space. One of the things that's kind of odd is if we just start talking about, let's say, the Pythagorean theorem, and we say, well, let's do things from the axioms up. Well, let's say we take as axioms set theory or something like this. Well, the Pythagorean theorem is really pretty complicated to prove in terms of set theory. I think it takes about 5,000 lemmas in this particular case. But the issue is, do we do mathematics at the level of those axioms, or do we do it at the level of the Pythagorean theorem? One of the surprises is that it seems to be possible to do mathematics just talking about the Pythagorean theorem. Not every time we talk about the Pythagorean theorem, worrying about exactly how do we define real numbers, exactly what are these very detailed underlying issues. It's very analogous to something else I was talking about, which is fluid mechanics. It might be the case that to describe how fluid works, you couldn't do it at the level of velocities of fields and so on, that you would have to go down to the level of molecular dynamics. You would have to look at how each molecule bounces around to know what the fluid as a whole does. That will be analogous to saying, well, you can't talk about the Pythagorean theorem, you have to talk about all those lower-level axioms. So it is a very interesting fact about mathematics that it is possible to do higher-level mathematics, that there is kind of a fluid dynamics level of mathematics that isn't down at the level of these individual axioms and so on. And one of the things that is rather interesting, I think, is that if we think about mathematics, we think about what's the limit of mathematics. You know, in the literature of mathematics as exists today, there are 3 or 4 million theorems that people have written down. But what's the limit as you go to an infinite number of theorems? You have this kind of metamathematical space, this sort of limiting metamathematical space. What is it like? Well, turns out the space of all possible mathematics with all possible axiom systems and so on is none other than our friend the ruliad, the same object that we're talking about as the foundation for physics. So the ruliad is the object that you get by looking at all possible mathematical theories and working out all their possible theorems and so on. And then the question is, well, what do observers like us doing mathematics, what is our perception of this ruliad, this thing that represents all possible mathematical theorems and so on? What we realize is that this kind of idea of being computationally bounded observers, there's some slight differences in the way it works, but basically the idea is that because mathematical observers of the ruliad work the way they do, it is inevitable that we will get a mathematics that we can do at the level of talking about the Pythagorean theorem rather than at the level of having to sort of drop down to these axioms. So in a sense, the possibility of doing high-level mathematics is the same phenomenon as the possibility of thinking about continuum space, for example, rather than having to go down and talk about the atoms of space. There are lots of wonderful analogies you can make between metamathematics, foundations of mathematics, and physics. So I'll give you one example. A black hole in physics is a place where you have an event horizon and so on, but in the simplest form of black hole, one of its characteristics is that time ends. After a finite, time always stops. In our models, it's very direct. At the center of a Schwarzschild black hole, in our models, they're simply these rewrites that define the progress of time. Simply, there aren't any more rewrites to do. So time stops. Okay, well, what's the analog of that in metamathematical space? The analog of that is, I think, a decidable theory in metamathematical space. In physical space, most of the time, most paths that you take in physical space don't stop. You can just keep going forever, winding around. That's analogous in metamathematics to having a proof that can be arbitrarily long, that never kind of terminates. That's analogous to having an undecidable theory. That's the kind of thing Gödel's theorem talks about and so on. It's the generic theories are undecidable in the sense that they have arbitrarily long proofs. But what one's saying is that the analog of a black hole in physical space is a decidable theory that has proofs of limited length. And actually, there are all kinds of other analogies one can make about the inevitability of space-time singularities and the inevitability of building up decidable theories. But in any case, the main point is that there's this amazing unification between kind of ideas in mathematics, ideas in foundations of physics. Another one I might mention, in physics, one of the obvious phenomena is that motion is possible. You can take an object, you can move it somewhere else, it's still the same object. Not obvious that would work. If it's all made of atoms of space, it could be the case you move it from here to there, and it's just a completely different kind of thing. But we know that pure motion is possible in physical space. What is pure motion in metamathematical space? It's transporting yourself from one kind of mathematical theory to another, let's say from algebra to geometry. The fact that you can say the same kinds of things in algebra and in geometry is kind of the analog of motion in metamathematical space. And one of the things that's emerged in mathematics in recent years is this kind of correspondence between different theories. I think that is a consequence of a kind of homogeneity in mathematical space. All right, let me quickly talk a little bit about biology because it's something I've been working on recently and you might find interesting. So it's going to turn out that the reason biological evolution works is another one of these stories about the interplay between computational irreducibility and kind of the computational boundedness of something like an observer. But let me talk about sort of basic biology. This is a very idealized biological system. It's kind of got a genome on the left that's just a cellular automaton rule, and it's got the phenotype, the creature growing on the right. Starts off from that seed as one red cell at the top, grows for a certain number of steps, then dies out. Okay, let's say we want to do mutations to the genome here. We're going to make random mutations. We're going to change the bits in that genome in a random way. And let's say that we have a goal of having a pattern that lives as long as possible, but not an infinite time. So this is a kind of a version of sort of idealization of evolution. This is now in successive rounds of evolution. There are red dots that show how long the thing lived. Much of the time, the red dots are kind of below the line, and it's losing out. It's not making progress. But occasionally, there'll be kind of a breakthrough, and the thing will live longer. It will have a new idea for how to live longer, and it will sort of progress. So here's an example of what happens in this particular case. These are kind of successive breakthroughs. And we can kind of imagine, if you have the fossil record or something, you can see, back in the Devonian period or something, you had one of these, and then later on you realize it built on the ideas that it had, made something else. If you roll the dice again on this on these mutations, you'll get sort of a different progression of structures that you get, but again, sort of building on what came before. Well, this is, so I think this is kind of a simplified picture of biological evolution, but you can kind of ask why does it work? Why is it possible to make progress? Why is it possible to come up with this very clever technique, so to speak, that thing there used to be able to live a long time? How did it figure out all that clever stuff? And can you always figure out clever stuff? Well, you can make what we call a multi-way graph, just like in the physics project, for all possible mutations of that biological system. And what we're seeing is different branches here are kind of like different pieces of the tree of life. There's a different set of discoveries that got made on one side versus the other. And the question then is how, and we can make bigger versions of this and so on, is we're thinking about sort of why does biological evolution work? Well, essentially we have a set of possible mutations, and we're saying which ones correspond to fitter mutations. The basic point is that when the fitness function is computationally simple, because of the computational irreducibility of what's happening underneath, it's with overwhelming probability possible to make progress. Let me make that simpler. If every organism, as soon as it was born, had to be able to compute the 10 billionth prime and do this or that to it, no organisms would ever survive. It's because the fitness functions of organisms are fairly coarse that it is possible for the organism to kind of survive, build on what it produced, and so on. So it's kind of this interplay between sort of computational boundedness of, in this case, the constraints and what's possible underneath. I said I would say something about AI, and I should just mention something about neural nets. The sort of a question, just like we're asking why does biological evolution work, we can also ask why does machine learning work? Something you would have thought people would know by this point. By the time $1 trillion has been put into it, you'd think somebody would have answered that question, but they haven't. This is a typical neural net that was trained to go from its input to output and compute that function. Well, one of the problems with the neural nets, it's kind of hard to visualize what's going on in them. These are a few pictures of that. But you can make much simpler versions of things like neural nets, where you have just a grid of artificial neurons. Or you can even go further and you can say, I'm just going to have a grid of cells. At every cell, I'm going to run one rule or another. That's my analog of having weights in my neural net. Well, you do that, and you can essentially do the same kind of thing that I was doing with biological evolution, where you can kind of flip bits, now not in the underlying rule, but in this array of cells. You can flip bits to try and achieve some objective. In this case, I was trying to make the initial pattern live for 50 steps and then die out. So the big thing to notice here is that we're kind of doing different runs of how does it manage to succeed in living for 50 steps. Let me just, I'm going to just make one comment about machine learning, and then maybe I don't get to talk about the stuff I just figured out in the last few weeks about biology, but maybe somebody can ask about it if we have a chance. The main point here is that this story about, in some cases here, you can kind of see mechanistically what happened. How did it manage to do what it did? In most cases, you can't do that. And you end up with these sort of irreducible computations. The big point here is that what is machine learning actually doing? It's basically cobbling together lumps of irreducible computation in a way that happens to work for the purposes you want. And it works because the purposes you're trying to define are very coarse compared to the sort of underlying computational capabilities of the system. So, analogy. Let's say you want to build a wall. That's your objective, is to build a wall. One way you can do that is you make bricks and you make some very, precise engineering structure to build up your wall. That's kind of a traditional engineering approach. The machine learning approach is you just look for rocks that are lying around on the ground. You put them together in whatever way they fit together, more or less, to make a stone wall. And that's kind of that's the way to think about what's happening in machine learning, is kind of taking these lumps of irreducible computation, fitting them together to achieve these fairly coarse objectives that we define as our fitness functions and so on. And so that kind of tells you things about what is the fact that you're not likely to be able to find interpretable things going on, because just like it happened to be this kind of rock, not another. Okay, just to wrap up here, I mean, I was teaser for one of the things I've been interested in recently is what is life, what is special about biological organisms, one of the things that have been discovered from molecular biology is that in biological organisms, molecules just don't just bounce around randomly. They're kind of actively transported to do the things they do. I think I figured out now a theory of how that works that is sort of analogous to statistical mechanics, which is a theory of sort of molecules just bouncing around randomly. It's a theory of what one might call bulk orchestrated matter. It's a theory of matter that has the feature that ultimately an objective is being achieved on a large scale. What consequences does that have on a small scale? But that's a coming attraction, and I'm hoping actually in the next few weeks I will finish that project. All right, I should wrap up here. Thank you very much.
Thank you very much, Steve, for an inspiring lecture, and even if it was disturbed. Now we have a big problem, is that this auditorium is going to be taken over by another big crowd. So we have time for only 2 questions. Yes, there's a microphone coming to you.
If you make the question short, there's a possibility I'll be able to answer it in a short way, but I don't guarantee it. Go ahead.
Thank you so much, Professor Wolfram, for such an illuminating talk. I will ask a question about origins of life and whether or not we think cellular automata and are essentially Vapnik shards and hyperparameters can ever model real-life biochemical molecules.
I don't know yet. So it's on my agenda to try and figure that out. I don't know yet. So that was a very minimal question. Sorry. Please.
I'm wondering why you have to sort of wait. If you can see the continuum effects of the sort of discrete nature of space at this scale, why you have to wait to get to such a large scale before you start to get any evidence of this sort of like heat-like phenomena, like why it's
perhaps you don't. I mean, really, let me explain. There's a lot of mathematics that one has to do to go from this very low-level hypergraph story to a story of something like continuum space. So in particular, we're trying to build what we call infrageometry. In ordinary geometry, things like differential geometry, you start from manifolds and things. Microscopically, a manifold looks like Euclidean space. In our case, we're trying to build a geometrical object where microscopically it looks like a hypergraph, not like a discrete hypergraph, not like something like Euclidean space. There's a whole bunch of mathematics to do to figure out how that works. For example, we have to know what is a curvature tensor in 3.1 dimensions. Nobody has any idea. This is something we have to build completely from scratch, and we've been steadily building this, but you kind of have to build these things to have a solid idea of what happens. The other thing is these simulations are not easy to do. We've been trying to sort of, recapitulating what the universe does. The universe computes at a very rapid rate. We're trying to catch up with that. And we can only, there's a bunch of technical issues about, GPU programming and so on to just get any kind of reasonable size simulation going. So you're saying we should go faster. We're trying to go faster, but it's just challenging.
That's not quite what I meant. What I meant was the fact that at this scale in which we live, humans, we can see we can see the effects of assuming that space-time is discrete, and
yes.
Then at a macro level becomes continuous. At our scale, we can, as far as we know, we can see the continuum effects of just. It's large enough to see the continuum effects of the scale of us looking at discrete space-time, but not large enough to significantly feel the effects of this sort of like randomness that is dark matter. I was wondering why the scale at which we have to observe things has to be so large before it starts to become significant.
I don't know.
Okay.
I don't know. I mean, I think that the question of whether we will be able to detect, the discreteness of space in a short amount of time is an interesting question. I mean, people with molecules were really lucky at the end of the 19th century that molecules are big enough that they could see them at that time. Actually, they were unlucky in the following sense, that Robert Brown of Brownian motion had done his experiments in botany in 1827. And it wasn't until basically 1900 that people connected that with actual molecules bouncing around. So, in modern times, one of the things I've been trying to do is there are various effects that we should expect based on things like dimension fluctuations and so on. It is my hope that actually using LLMs and things, one can sort of thematically search the existing physics literature to basically archaeologically find effects that people barely reported because they were so weird, that are signs of that kind of thing. Rather than saying, do an experiment now, spend $1 billion on it, we can just go back and look at what has already been done. That's the hope. Hasn't been done yet, but I hope in the next few years we may be able to get to that. Maybe we have one more quick question if
You're going to fight with a big crowd, so a quick one.
Okay, how about?
Does the ruliad have any predictive powers, and will it have any predictive powers?
Yeah, I mean, so I think very much so. I mean, all of these statements about discrete space and so on, these are all kind of, I would say, consequences of this ruliad idea. Now, the thing that's tricky is, for example, why are the number of dimensions of space 3 for us? My guess is that's a feature of the way we are as observers. So there are things that and as we learn more, as we get a better idea of how to parameterize our nature as observers, we will be able to probe more aspects of how the ruliad works. But the ruliad it's very rigid in the sense that there is just one of it, and you can start doing all kinds of math and computation and so on to work out its consequences. There's no wiggle room. You don't get to say, whoops, we make a small change here. It's a very rigid kind of theory. The part that is tricky is how we perceive what is happening in the ruliad, and that depends on sort of our model of our nature. So for example, very simple example, the fact that we have an idea of space is a consequence of the fact that we have the characteristics we have. Like I look around this room, I can see maybe 10 meters, 20 meters or something away. Light comes to me from the other side of the room in a microsecond. But my brain processing is on millisecond timescales. So for me, I look around, at every moment, there is the state of space at a fixed point in time. If I thought 1,000,000 times faster than I do, I wouldn't have that view that there's just this state of space at a particular time. So a lot of aspects of the way that we perceive the universe depend on the way we are. And I think that's that's the place where there's lots to be figured out about that. And my guess is that there's some super obvious feature of the way we are as observers that causes us to parse the universe as a three-dimensional space, as opposed to just saying, well, we know, we could imagine we're just like Turing machines where we're running around in one dimension, kind of just sampling what happens in space. But we don't. We have the idea that it's three-dimensional, and I suspect that's a feature of the way we are. But yes, there are lots and lots of things. I mean, not only on the practical side of physics, there are also predictions about mathematics, et cetera, et cetera, et cetera. It's a very rich kind of thing, and we should stop.
Yes, yes. Thank you very much again for this.
Okay.